as Peter was asking, why would you want to include, why would you want to do things as a regression? Well, nuisance covariates is the main reason. And there are a few different ways to go about this, and it kind of depends on what kind of test you're going to use. So we've gone back and forth on this a few times, and part of the reason is if you plan to do a permutation tests are notoriously difficult when you have nuisance variables, and the best way to carry it out is to actually regress the nuisance covariate out of both your dependent and your independent measures, and then do the permutation test using a simple model that only has the two variables. So we can do that fairly easily. Let me create a nuisance covariate using VLSM. VLSM is a program that creates random data. So if you ever need to convince yourself of something, it's actually a very useful tool. So now we've created this nuisance.ref, which looks like that. So it's random data with a mean of 10 and a standard deviation of 2 or something like that, or looks like something like that. VLSM has a few other arguments that can create random 3D volumes and so on. All right, I'm developing too many windows. Okay, so now what we can do is use VB-VOL-regress to actually factor that nuisance covariate out of our continuous measure and our lesion data. Like I said, VB-VOL-regress doesn't care if things are 1D or 4D, if they have spatial extent or not. So either of these will work, and it has an option to, instead of producing the stat map, to just produce the residuals. So that's what we're going to do. In this case, we're going to send the residuals from the dependent measure to a file called dv2.ref, and the residuals from the independent measure to iv2.ref. So I'm just going to run both of those commands really quickly. Now I should mention that although this is the best approach for running a permutation test with a nuisance covariate, it's not considered to be perfect or exact. It's just the best you can do. There isn't a general theoretical solution for that. But now that we've done that, we can run VB-VOL-regress. We can do that to run the regression using our dependent measure and our independent measure with that stuff factored out. And we can look at those, by the way, to see what factoring out a random variable has done to the data. So, for example, here's our original continuous thing, and here's our one that's that has that thing factored out. And you can see that they're completely different, but let's look at the correlation. So the correlation is 0.99. So the scaling got completely readjusted, but they're actually very highly correlated, which you would expect after factoring out completely random data. So now we can actually factor out. I mean, we can actually carry out that regression using the reduced variables. I'm not going to do the permutation test because there's no point to it. But so we've now produced a volume called new tmap1 that is the regression with this random covariate factored out. If you're not going to do a permutation test, then there is an exact solution, and that's to just include the nuisance covariate as you would in any multiple regression. So you can see on this command line there are two IV arguments, continuous.ref and nuisance.ref. So we're including them both, and in our contrast we're saying we still want to wait. We want to look at continuous.ref, but the other nuisance.ref and the intercept are still in the model. So there are now 3 terms in the model, but our continuous dependent measure is still what we're interested in. And we're going to put the map file in new tmap2. Okay, let's run that. Okay, so how did we do? It's an interesting question because we've now factored this nuisance covariate out 2 different ways, and it shouldn't have had a huge effect on the model in general. So how did these two methods of factoring out the nuisance covariate do in comparison to each other? Again, 2% of the voxels were different. That's not surprising. You'd expect every voxel to be affected a little bit. The mean difference is fairly small. This is not a big difference in t-value. The maximum difference, also fairly small, but not completely meaningless. You can imagine this making the difference. we can also do the other two pairwise comparisons between our original T-map and the two different methods of factoring out the nuisance covariate. I don't actually know that these are that meaningful, but at least you can reassure yourself that that they're different, and they're different by the same magnitude. So clearly, even this sort of random covariate has had an effect on the T-map. We have a mean difference in t-value of 0.09, but in some voxels the difference is as high as about 1. So even factoring out nuisance covariates is not always completely without, factoring out random nuisance covariates is not without effect. So that's just sort of a sampling of various things that you can do at the command line in VoxBo and to do these analyses. None of them are that conceptually complicated. In many ways, in most ways, they're much easier than doing image analysis for fMRI, mainly because there's no autocorrelation, so the statistics are exactly what you're used to from other domains. In many ways, simpler. But just because you're dealing with a lot of 3D and 4D data, and you're dealing with kind of arcane commands, because the SPSS, which if you're used to SPSS or R, those programs don't handle image data. So there's a lot of nonsense that surrounds it in terms of getting these programs to do the right thing. And I think in many ways it's also a good thing, because like people who use R, I think people who use VoxBo and to some extent MRI-Cron as well, really do spend a lot of time using various tools in the software to examine their data and check and recheck their assumptions. So that's the end of the part where I'm going to be actually typing commands, and then I have other topics that I wanted to get onto in the remaining time if we can. But are there any questions about that all that stuff? Any other things that you'd like me to try to do with this nonsense data before I move on?
I just thought it might be useful to just go over slowly again the issue of the two ways of factoring out the nuisance covariate.
Yeah.
I just wanted to make sure. In one case, you residualize the nuisance covariate, and you did it from both the dependent and the independent variable.
Yeah.
Which is different, I think, from what most of us are used to when we think about that. Certainly, when we published this, we residualized it just from the independent variable.
Yeah.
Right. But you recommend doing it.
Yeah, and it's not really. It's not my recommendation exactly, but there have been articles where people have carefully evaluated a bunch of different proposals for how to do this best, and this is kind of what they came up with. And in retrospect, it's I'm not going to say obvious, because some of the other options were sort of subtle, but it's probably obvious compared to what we were doing initially, because when the sort of intuitive thing is to remove it from the dependent variable, I guess. Does that seem most intuitive? Because the idea is you don't want to be explaining anything having to do with this nonsense. I guess depending on is that more intuitive?
Independent can't explain.
Oh yeah. Okay, so yeah. So the more intuitive way is to factor it out from the independent variable, right? Because you're trying to say, what can not just what can A explain, but what can A explain, independent of whatever A shares with B.
Just a minute. The independent variable here is the lesion. So we've not done that in the past. So we've factored it out of the dependent variable.
Oh, okay. Wait. Okay. It turns out, yeah.
Obviously not, yeah. But we have. I think.
Whichever way is more intuitive. Either way, if you factor it out of just one, okay. If you factor it out from just the dependent measure, then what happens is you have excess variance in your independent measure that's not doing you any good. So you can actually reduce the variance by factoring out of your independent variable as well. You can reduce the variance there that isn't going to end up explaining any of the variance. Correspondingly, if you factor it out of just the independent variable, then you have extra variance in the dependent variable that you already know your independent variable is not going to be able to explain. So it doesn't really make that much sense to factor it out of just one. In practice, it doesn't turn out to be a huge deal, but if you do one, you should do the other.
And then in the other case, you just use the regression. Model. And then how exactly is that calculated? What did you standardize the beta weight? I mean, you're still winding up doing a t-test.
Yeah. So it's
pretty basic, I know, but I don't.
Yeah. Well, when you carry out a regression, you get weights on all your covariates, and by scaling them to the error, you get a t value for you can get a t value for each covariate. You can also, if you want to, by clever use of scaling, get t values for comparisons between your different covariates, which we often do in fMRI. But in this case, it's a very simple case. We're running a multiple regression, and we're interested in the t value associated with just one of the independent variables. And I should add that if you use, for example, MRI-cron, there are some other statistical tests available in MRI-cron, like the Brunner-Munsell test, and for certain types of data, there's the Liebermeister test that are available for different situations. I don't find them to be. I mean, the Brunner-Munsell test tends to give you basically the same results as you get from a regular t-test, but there are obviously some cases where it's better. It's just not clear that those cases really come up that often.
If your dependent measure is categorical also, it's just ones and zeros, is there like a chi-square test available?
VoxBo does not have that. And oddly, nobody's ever asked for it. But MRI-cron has that. And you have I think it also has some alternative tests for that. Yeah. In some cases, I think you can use a regression for that kind of data, but so I've said a little bit about multiple comparisons, and there are lots of different ways of correcting for multiple comparisons. This is, of course, not peculiar to VLSM. This huge mess devolves to us from fMRI. I shouldn't say it's a huge mess. It's only a small mess. The two sort of big categories are what are called family-wise error rate control and false discovery rate control. And family-wise error rate control, and somebody stop me if everybody in the room knows this, but I just felt it was helpful to go over it systematically. Family-wise error rate control is what we're all sort of used to from when somebody asks us to control multiple comparisons, which is basically what's accomplished by Bonferroni correction. You're making sure that the probability of seeing one or more false positives is below some rate. So instead of carrying out if you carry out 5 tests and each one has a false positive rate of 0.05, then the probability of seeing at least one false positive among the 5 tests is going to be above 0.05. So that might be undesirable if you're carrying out lots of tests. So family-wise error rate says we should make sure that the aggregate false positive rate is 0.05. False discovery. So that's what everybody's used to. That's what most people are taught in grad school. And the only new thing here is that we now have a. I'm not sure if I can call that an acronym. It's not really pronounceable, but we have an abbreviation for it anyway. False discovery rate, however, is a relatively new approach to thresholding that people are very excited about because they describe it as more powerful than family-wise error rate. And in some sense, it's more powerful in the sense that it gives you a reduced threshold and allows you to report voxels that wouldn't otherwise be reportable. But it's not more powerful in the sense that it lets you report the same thing with more power. It's more powerful because it's more lax. It's a different standard for false positives, and the standard is just that it controls the proportion of false positives. So at a typical false discovery rate of 0.01, it means that you get to report lots and lots of voxels, and